Hello, welcome to another week of Math 105. So we're into chapter 6. Just want to jump right in. Actually, I should tell you, I got all your tests. They're in my emails, so I'm just going to print them off and grade them like we talked about, and then I'll email them back to you individually with a grade report to where we're at as of now. So should be expecting those this week. Cool beans. Okay, dokey. Get rid of this. Ooh, I want to save that. Gotta take a picture of this because I want to save it. I'm working on some music. Okay. Chapter 6. All about radicals. So we've been talking about square root, cube root, fourth root maybe. I'm just going to write fifth root here just to make a point. And then, normally people would do like the nth root, where you just write n there to say it could be anything. N could be any number, any positive whole number. You're never going to write a negative in here, so the negative 5 root, that doesn't make any sense. That's just not something that you ever see. A 0 root would also be very weird, that you'll never see anything that looks like that. So you're only ever going to see positive whole numbers in this little nook. If you don't see anything, it's assumed to be a 2. So here's another thing that you'll never see. No one ever writes the 2 in there. Just one of these things, it's so common that when it's not there, that's what a square root is. But anything other than 2 needs to be written explicitly so that you know what it is. So hopefully at this point you've begun and can do things like this pretty easily, things like this maybe. That's a stampede there. Things like, just trying to think of a bigger one, but, So hopefully you can have some of the perfect ones memorized, right? This is 3. Square root of 9 is 3. Square root of 8, cube root of 8 is 2. Fourth root of 16 is 2. Stuff like that. So we talked about rational exponents last time, and so hopefully at this point too you can do things like this, where maybe you can take 16 to the 3/2 power. So there are a couple things you might be asked to do with something like this. You might just be asked to simplify it. Or, alternatively, a really common kind of thing is just to say, hey, take this and rewrite it using radicals rather than a rational power. So I like to draw the analogy between mixed numbers and improper fractions. If you have a mixed number, you can take that always and represent it as an improper fraction, right? So you can write 2 2/3 as 8/3. These are the same number, and it's kind of like just depends on what you want to do, and it depends on what you want to see. It's exactly the same. Nothing changes. You'll never be in a situation where one doesn't work where the other does. It just is completely up to you on what you want your work to look like. And it's the same thing here. If you have a rational power, you can always transfer that into radicals. It's not changing anything. It's just changing the way that it looks. And the reason you would want to do that is just for like aesthetical purposes. If sometimes it's easier to see things in terms of radicals. Sometimes it's easier to see things in terms of exponents, rational exponents. So, if I was simplifying this, maybe the first thing I would do is transfer it into a radical. So this would be the square root of 16 to the 3rd power, right? The denominator is the root, and the numerator is the power that you put on your thing. Alternatively, though, I was saying there's this other format. You could have written this as the square root of 16 all to the 3rd power. And I probably would do it this way if I was simplifying, because now I don't need a calculator to do it. I don't know what 16 cubed is off the top of my head, but I do know what the square root of 16 is. It's 4. And 4 to the 3rd power is 64. So 16 to the 3/2 power is 64. You should use your calculator to prove that to yourself. Do 16 raised to the 3/2 power. Be sure to bracket it, and prove to yourself that it is 64. Cool. On the homework, hopefully we're practicing other types of things that were just completely generalized. So maybe like x to the 2/7. If you just have x to the 2/7, then you could write that as the 7th root of x squared. Yeah. Or you can take the 7th root of x squared and write it as x to the 2/7 power. So yeah, that's useful to transfer back and forth. Sweet. All right, where we left off was in 6.3, where I was talking about how to simplify square roots. So I just want to make this point again, where let's say you have the square root of 25. That is a perfect square root in that this can be simplified to exactly the number 5. Boom. It is 5. The square root of 25 is the number 5. They're the same number. Okay? Exactly the same number. Boom. But if you needed to do the square root of 24, there is no there's no whole number that simplified that when squared will give you 24. So what this is asking you is, what squared is 24? So you have a couple options. You can either approximate this using decimals, in which case you'll need a calculator, or you can do sometimes a perfect algebraic simplification. And that's this process that we were talking about. In order to do that, you need to know that the square root of two things multiplied together can be broken up into individually the two things being multiplied together. Right, so really this is just saying if you have multiplication underneath a square root, then you can break that into two square roots being multiplied. Or if you have two square roots being multiplied, you can combine those into one square root with a multiplication underneath. So this goes either way. It's useful both ways. In this case, you can use that to say the square root of 24 is 4 times 6. 24 is 4 times 6. Now this property tells you that this can be written as the square root of 4 times the square root of 6. And we know that the square root of 4 is exactly the number 2. So what's happening here is that you can see that the square root of 24 is the same as 2 multiplied by the square root of 6. So just like usually the language that I use and I've heard other people use is that 24 contains a factor that is a perfect square. And when you have a perfect square underneath a square root, it can be removed as a whole number. So what we're kind of like, what I say is I pulled out a 2. I can pull out a 2 from 24 because 4 is the square root, comes out as a 2. So, I might write that sometimes like this. You should be aware of what's happening and exactly how to justify that, right? And that's using this, break this into 2, square root of 4 is the number 2. But, once you've done this a bunch, you'll see that it's just kind of like, you take the 4, and the 4 underneath the square root is a 2 on the outside of a square root. Yeah, so let me make this point really clear too. The square root of 24 is the same as 2 times the square root of 6. Exact same number. Again, you should use your calculator to prove that to yourself. Do the square root of 24 on your calculator, boom, you'll get a decimal approximation. Then do 2 times the square root of 6 on your calculator, boom, you'll get the exact same decimal approximation. It's the same number. This is the simplified, fully simplified, perfect version of the square root of 24. Cool. Another point here to make is that this whole process, what you're seeking to do is take out a perfect square from a square root. So 24 could also be written as 12 times 2. And then you can use this property to say that that's the square root of 12 times the square root of 2. Right, but neither 12 nor 2 are perfect squares. So it just doesn't help you. Right, so I sometimes like to say what you're doing here is you're looking to break up the number into two numbers where one of those is a perfect square. So that's why it's nice to have the perfect square list. 1, 4, 9, 16, 25, 36. You know, have hopefully memorized like the first 12. I would say the first 12, maybe the first 15 perfect squares. Is really nice. Cool. So let me give you one to try here. Try this. Try the square root of 120. So it just says simplify normally. You know, it'll just say like simplify using factoring, it might say, because you're going to factor 120 into two numbers. And you need one of those numbers to be a perfect square. And then the reason you do that is because then you could remove that from underneath the square root. So 120 is 10 times 12. But again, neither 10 nor 12 are perfect squares. So that's probably a bad choice. So I might say 25. Calculator. It's really nice to have a calculator on hand here when you're doing this. You can just start running through things. 120 divided by 36. Nope. 120 divided by 4 is 30. So you could write this. 120 is 4 times 30. Now you can use this property to rewrite this as the square root of 4 times the square root of 30. And the number, square root of 4 is the number 2. So look, I'm just going to pull and move here. What I've really written is the square root of 4 multiplied by the square root of 30. But the square root of 4 is the number 2. So I'm just going to magically change that to the number 2. So the answer is 2 root 30. I'm just thinking if 30 can be simplified even more. 30 divided by 4, nope. 30 divided by 9, that's going to be 9. Or 16, good. So there you go. 2 root 30 is the full answer. Great. So again, 2 root 30 is exactly the same number as the square root of 120, just the simplified version. Awesome. Okay, another thing that is going to come up is just simplifying things like this. So we talked about this a bit in the beginning. We're assuming all variables represent positive numbers throughout the whole chapter 6. And when that's the case, squares and square rootings cancel each other. So the square root of something squared is just your thing, x. Cool. But what about the square root of x cubed? Well, you can do a similar process where you write x cubed as x squared times x. X cubed is x squared times x1, right? Then use this property to break this into the square root of x squared multiplied by the square root of x. So I'm splitting this using this property. And now we know that the square root of x squared is just x, and the square root of x, there's nothing you can do with that. So it's x multiplied by the square root of x. This can get really confusing once you're getting used to this notation, right? So x multiplied by the square root of x, just, it kind of gets, there's a lot of x's going on. But I do want to make a point that x is a different number than the square root of x. Right, so these are two totally different numbers, and what you're doing is you're just multiplying those numbers together. So it's like saying 2 times the square root of 2. or maybe like 4 multiplied by the square root of 4. If x was 4, then x root x would be 4 times root 4, which is 4 times 2, which is 8. You know, so x and the square root of x are 2 totally different numbers, which can get convoluted. All right, so using that same kind of idea, try to simplify the square root of x to the 8th power. So simplify that as much as you can. Pause the video if you'd like to give it a try. What I would do is I would factor this. So there's 2 ways that I know how to do this. You could either write x to the 8 as x4 squared, using the properties of exponents, right? And now you can see that you have something squared under a square root, so the square and the square root cancel each other, and you just get x to the 4th power. Another way that you could do this is that you could factor it into x squared times x squared times x squared times x squared. You can multiply x squared times itself 4 times, then use the property to split this up into 4 different things. Square root of x squared times the square root of x squared times the square root of x squared times the square root of x squared. And now each one of these is the number x. Right, so this is x times x times x times x, which is x to the 4th power. Either way, the answer is x to the 4th power. There's 2 ways. There's 2 ways that I would normally use to justify that. I'm sure there's other ways to justify that as well. There's a trick here to this, and hopefully if you do a bunch of these, you can start to see that when you're simplifying a variable to a power, all you really have to do is divide whatever root it is into that number. So 8 divided by 2 is 4. Right, like if this number was a lot bigger, let's say this, simplify the square root of x to the 80th power. So I know that the answer is going to be x to the 40th power, and that's because 80 divided by 2 is 40. But if you wanted to justify that, you could rewrite x to the 80th power as x to the 40th power squared, and then cancel. Cool. So that's all well and good if you're talking about square roots. What if you're talking about cube roots? Let's say cube root of 16. Here's a really common mistake that I've seen a lot, is 4. But that's wrong, right? Because this is a cube root. The square root of 16 is 4. Cool. But the cube root of 16 is not equal to 4. This is asking you for a number to the 3rd power that equals 16. And 4 to the 3rd power doesn't equal 16. So, what you got to do is use this factoring process. Before, when you were talking about square roots, you're looking to break this number into 2 numbers, where one of those is a perfect square. Now what you're doing is breaking this into 2 numbers, where one of these is a perfect cube. Right, so it's nice to have a list of perfect cubes, 1, 8, 27, 64, 125, probably up to the first 10, maybe even the first 15 perfect cubes listed out, so that you can, refer to them as you're doing problems like this. So what I would do here is break 16 into 8 times 2. And that's because 8 is a perfect cube. Now you can use this property to rewrite this as the cube root of 8 multiplied by the cube root of 2. The cube root of 8 is the number 2. The cube root of 2 just stays the way it is. So the answer is 2 multiplied by the cube root of 2. So again, just to make this point, the cube root of 16 is exactly the same number as 2 multiplied by the cube root of 2. Use a calculator to prove that to yourself. Same number. All you're doing is simplifying it into a different form. Cool. So let's see here. Try this. Try the cube root of 192. Try simplifying the cube root of 192. So look, let me give you a hint, or kind of like a process. Here's the process that I do when I'm simplifying any root like this. It's a cube root, so I'm going to try to split it into two numbers, and I want one of those to be a perfect cube. Right, so I need to factor 192 into something multiplied by something else. And I want one of those things to be on the list of perfect cubes. So I'll go to my list of perfect cubes. 1, 8, 27, 64, 125, what's 6 cubed? 216, 7 cubed is 343. And this is what I do. I don't start from the top and look down. I start from the bottom and look up. Because what I'm trying to do is find the biggest number that is a factor of 192 that's on this list. So I'll just go like this. You don't have to worry about 343 because it's bigger than 192. Don't need to worry about 216 because it's bigger than 192. Does 125 divide evenly into 192? No. Does 64 divide evenly into 192? Yes. 64 times 3. So I'm splitting 192 into 64 times 3. Now I can apply this property to say that that's the cube root of 64 multiplied by the cube root of 3. Right, I'm just splitting this. And now the cube root of 64 is 4. This is 1, 2, 3, 4, 5, 6, 7. That's why it's nice to have this kind of like gridded out and listed so you can just constantly reference it. The cube root of 64 is the number 4, and the cube root of 3 is the cube root of 3. So it's 4 multiplied by the cube root of 3. Again, same number as the cube root of 192, just simplified. Cool. All right, now I'm just going to give you one other, just kind of like, kind of challenge problem. Like, just see if you understand this. Let me make it up real quick. Let's say 486. Try the fifth root of 486. Try to simplify the fifth root of 486. So take a second to see if you can work that out. I'm just going to go ahead and do it, so pause the video if you want to try. It's a fifth root, which means in order to simplify this, you're going to need to bust this into two numbers. And you want one of those numbers to be a perfect fifth. So what you should do is create the list of perfect fifths all the way up to until it's bigger than 486. So 1 to the 5th power is 1. 2 to the 5th power is 32. 3 to the 5th power is 243. 4 to the 5th power is 1024. So now you can stop because you've gone beyond 486. And then you just want to figure out which one of these divides evenly into 486. And I like to start from the bottom so that I can capture the largest number, because there could be more than one number that divides evenly into it that's on the list. But I want to find the biggest one. So 243, 486 divided by 243 is 2. Yeah, so that divides evenly into that. 243 multiplied by 2. Now again, use this property to split it, into into two fifth roots. So I'm just splitting that right down the middle. These two things are being multiplied together. The benefit of that is that the fifth root of 243 is 3. So it's 3 times the fifth root of 2. Yeah, so you can do that with any root and with any number. So all roots, all radicals of numbers have a most simplified form. But here I want to make a point that it's not always possible to go further, right? Like, take for instance the square root of 10. So what we're just talking about is to find two numbers that multiply to 10, where one of those numbers is a perfect square. So the perfect squares are 1, 4, 9, 16, 25, yada, yada, yada. But you don't have to go any further than this because those numbers are bigger than 10. 9 does not go into 10, 4 does not go into 10, and 1 isn't helpful. So there is no perfect square that's a factor of 10, which means that that one's done. That's it. That's the simplified version of the square root of 10. That's as far as you can simplify that. So sometimes that happens. So the point I want to make is that it's not always possible to do this. It's not like you can do this with every single number. Some numbers are, that's just the way it is. So, yep, great. Okay, another way that this can go is that you can have these at the same time. So you might see something like this. The square root of 32x4. So a couple ways to do this. But what I normally do is I focus on the numbers and the variables separately. So if I was doing this, I would first act like it was just the square root of 32. And bust 32 into two numbers, one of which is a perfect square, so 16 times 2. Then once I've done that, I'll act like it's just the variables and do the same thing. I would break x4 into x2 times x2. And now I just remove what I can. So 16 under a square root comes out as 4. An x squared under a square root comes out as x. And an x squared under a square root comes out as x. So you get 4 multiplied by x multiplied by x multiplied by the square root of 2. And that's it. So you get 4 times x times the square root of 2. And 4 times x can be written as 4x squared. So it's 4x squared root 2. And remember, all these numbers are being multiplied together. 4 multiplied by x squared multiplied by the square root of 2. Great. All right, that's about as difficult as it gets for those simplification problems. You just have to practice those a bunch. So that's what homework's for. You know the deal. Great. All right, so the rest of the chapter is kind of in preparation for solving radical equations. And you know, like, this kind of outline that I've been giving quite a few times for what algebra is like we've talked about simplifying radicals. And now really what you want to do is learn how to add, subtract, multiply, and divide radicals. Then you're going to use all of these things to do what you really want to do, which is solve radical equations. So we should talk about how to add radicals, subtract radicals, multiply radicals, and divide radicals. Let's start with multiplication. How do you multiply radicals together? So let's take, for instance, the square root of 2 and multiply that by the square root of 5. Well, you just use that property that you were using before, but you use it backwards. The square root of something multiplied by the square root of something else is the square root of both things multiplied together underneath. So it's really simple, actually. You just go, boom, square root of 2 times 5, which is the square root of 10. One thing that should always be kept in mind is that when you combine radicals together, you should always try to simplify the result. So it's just like fractions. Always report your answer in its most simple form, right? So if this was, for instance, this, if it was the square root of 2 times the square root of 6, you'd get the square root of 12, and the square root of 12 can be simplified. So you bust it into two things, 4 times 3, and you remove one of those. So it's 2 times the square root of 3. So if you did have a question that said, hey, multiply the following radicals, the square root of 2 times the square root of 6, and you answered the square root of 12, you'd be right, but you wouldn't be 100% right, because the square root of 12 can be simplified into 2 times the square root of 3. So root 2 times root 6 is 2 root 3, once you've done all the work. Yeah. So give a couple of these a try. How about square root of 6 multiplied by square root of 7? And then try this as well, the cube root of 6 times the cube root of, let's say cube root 4 times cube root 4. So try both of these. Square root 6 times square root 7 will be square root 6 times 7, which will be the square root of 42. Can you simplify the square root of 42? That's what you need to determine before you're done. So, if I'm going to simplify the square root of 42, I'll get out my list of perfect squares. And I just start looking for things that go into 42 perfectly. 36 doesn't, does 16, does 42 divided by 16 work out? Nope. Does 9 go into 42? Probably not. Nope. So 42 is done. Nothing goes into 42. No perfect squares. 42 isn't a factor, you know. There's no perfect squares a factor of 42. So that's as far as you can go. Great. Cube root of 4 times cube root of 4 is cube root of 4 times 4, which is the cube root of 16. Before you answer that, you're going to need to know if 16 can go any further, so get out your list of perfect cubes. 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, right? You don't have to go any higher than the number you're looking for. 8 is a factor of 16, so this can be written as the cube root of 8 times 2, and then remove the 8 as a 2. So this is 2 cube root 2. Good. Point here is what happens if you have something like this? Square root of 6 times the cube root of 7. Can't do it. Right? This property really should be written like this. Really, you should write the nth root of A times the nth root of B is the nth root of A times B. If those numbers are different, there's no property that helps you do that. I mean, there is ways to do this. For our purposes in chapter 6, there's not a way to combine these. And for anybody, just out of interest, like if you wanted to, you could rewrite the square root of 6 as 6 to the 1/2 power. And you could rewrite cube root of 7 as 7 to the 1/3 power. And now there's some like algebraic trickery that you can do. Like you could write the 1/2 power as the 3/6 power, because 1/2 is the same as 3/6. And you could write the 1/3 power as the 2/6 power. And now you could factor out a 1/6 and write this as 6 cubed times 7 squared, whoops, all to the 1/6 power. And then you could write the 1/6 power as the 6th root. And if you wanted to do 6 cubed times 7 squared, you could do that. So, I mean, what I'm trying to say is that it is possible to combine the square root of 6 and the cube root of 7, but in a way that, to me, hasn't really ever been helpful. So, yeah, what I would do if I was you guys is, well, first of all, you're probably not going to see anything like this, from me in Math 105. But if you ever continue to Math 151 or beyond, things like this might come up. And what I would do, if it were me, is I would just evaluate whether or not, I want to combine them, and if that gives me any kind of benefit for whatever it is that you're doing this algebra for. See, later on, once you continue on with math, like if you go to calculus or if you take statistics, things where you're going to use algebra, it really just becomes a tool. Algebra is a means to an end a lot of times. So it's, there's not really ever, it's like you have to combine them, Maybe you would want to combine them because that's going to help you do what you ultimately want to do. But you don't, it's up to you to wield your tool belt in any way that you see fit, and that's what algebra is to me. It's just like, hey, here's some things you can do to make it easier or not. So, yeah, just to make that point clear, if you have different roots and you're multiplying together, we're going to treat that as like can't do it. But hopefully we won't. I'm not even going to put anything like that on the homework. So, sweet. All right. Yeah, that takes care of multiplication. Let's see where we're at here. It's about 40 minutes. So I'll talk about division and addition and subtraction, and then maybe we can call it a day. That's enough for practicing on the homework. So division is a bit trickier. So let me explain division in depth. Here's the thing about division of radicals. Let's say you have the square root of 2 divided by the square root of 3. Division, if you go all the way back to pre-algebra, and what dividing is, here's truly what's happening when you're dividing two numbers. So let me just bring up something else like 2/3. 2 divided by 3 means that you've taken something and you've split it into 3 pieces. The denominator tells you how many times to break one thing up. And then the numerator tells you how many of those pieces to take. So the denominator divides one thing into that many pieces, and the numerator takes that many pieces. So in that way, you have 2 of 3 of this square. You have 2 out of 3 pieces of this square. So it's almost like intrinsically in division that you need to divide something up into a whole number amount. Right? The square root of 3, how can you divide a square into the square root of 3 pieces? The square root of 3 is an irrational number. So the best you can do is estimate it with a decimal. You should do that. Estimate the square root of 3. So the square root of 3 is approximately 1.7320508088, but that decimal goes on forever. It's an infinitely repeating decimal, which means if you were going to bust this into that many pieces, you're going to have to approximate somewhere. So the point is that if you have a radical in the denominator of a fraction, that's a problem, right? But there is something that you can do to get rid of that radical, and it's called rationalizing the denominator. A radical is what's called an irrational number. So rationalizing the denominator means to take an irrational number and make it into a rational number. It's not that difficult to do. because you're always allowed to multiply a fraction by 1. So you can multiply anything on top and bottom as long as it's the same thing. So do the square root of 3. Square root of 3 divided by the square root of 3 is the number 1. When you multiply these together, you get the square root of 2 times the square root of 3, which is the square root of 6. And the square root of 3 times the square root of 3 is square root of 3 squared, which is just 3. Or the square root of 9, which is 3. So, you get the square root of 6 divided by 3. So here's another point to make. The square root of 6 divided by 3 is the exact same number as the square root of 2 divided by the square root of 3, but this one has a rational denominator, whereas this one does not. So that's how you divide radicals. Or I should say that, across all of math and algebra, if there is a radical in the denominator of a fraction, you should rationalize that denominator. Yeah, it's just one of those things that makes it technically correct and is very helpful. I've used this a million times. Rationalize the denominator comes in handy across the board. So, yeah, that's what you should do. So here's another one for you to try. Here's a way that you'll see things a lot. The square root of 1/2. Keep in mind that there's a second property of radicals, that if you have the square root of a over b, you can take the square root of the top and the square root of the bottom. The first property was the multiplication one that we've been using. So these are the two properties of radicals. This one comes in really handy with division, obviously. So if you had a problem like this and it asks you to simplify, the first thing you should do is use property 2 to say, well, that's the square root of 1 divided by the square root of 2. The square root of 1 is the number 1. So there's where you're at. But now you have a radical in the denominator of a fraction, which is a problem. You have to rationalize the denominator. How you rationalize the denominator is really, honestly, it's like deceivingly simple for square roots. You just multiply it by itself. The square root of 2 multiplied by the square root of 2 will be just 2. But you have to do that on the top as well, because you can't just multiply a fraction by anything. You have to multiply it by the number 1. So it's got to be the same on the top and the bottom. 1 times the square root of 2 is the square root of 2. And the square root of 2 times the square root of 2 is the square root of 4, which is just 2. So you get the square root of 2 divided by 2. On your calculator, do 1 divided by the square root of 2, see what you get. And then do square root of 2 divided by 2, see what you get. Should be the same number. It is the same number. This one has a rational denominator, which is advantageous. Great. Yeah, so that's rationalizing the denominator with square roots. So I'm going to bring up now the more complicated version of this, because I don't like telling people that and having them practice it 1,000 times. Because once you go on to cube roots, fourth roots, and fifth roots, you might do something that is incorrect. So try this. Try the cube root. Now let's try 3 divided by the cube root of 2. Alright, so you might see a problem like this that says rationalize the denominator. This is a fraction. This fraction has a radical in the denominator, so you got to rationalize it. If you get too used to rationalizing denominators of square roots, you might think that all you need to do is multiply this by the cube root of 2 on top and bottom. But give that a try. 3 times the cube root of 2 is 3 multiplied by the cube root of 2. And the cube root of 2 times the cube root of 2 is the cube root of 4, which is just the cube root of 4. That's not a perfect cube. So you still have a radical in the denominator. Didn't really do anything for you. So here's the trick on these, is with square roots, if you have, say, the square root of 5, you can make that a 5 just by multiplying it by 1 more. Square root of 5 times the square root of 5 is the square root of 25, which is 5. But if you have the cube root of 5, you can turn that into 5 by multiplying it by 2 more. So that you have a total of 3. Here with square roots you need a total of 2. With cube roots you need a total of 3. Cube root of 5 times cube root of 5 times cube root of 5 will be cube root of 5 to the 3rd power, and then these will cancel each other out. So you need as many as the root is. So easy fix for this. Multiply it by the cube root of 2 times the cube root of 2 on top and bottom. So what I'm saying is multiply in 2 more cube root of 2's so that you have a total of 3. So this will produce 3 times cube root of 2 times cube root of 2 will be 3 times the cube root of 4, because I combined these two together. Cube root of 2 times cube root of 2 times cube root of 2 is just 2. That'll be cube root of 2 cubed, and the cube root and the cube will cancel each other, leaving just 2. So there you go. Now you have rationalized the denominator. Some might argue that that is not as simplified as this. And, I think you can make a case for that. But the problem is with a radical in the denominator of a fraction. So we consider it simplifying because fractions should always have a rational denominator. So the final product might look more intense. It might not look as simple, but it is simplified. Cool. Yeah, great. All right, so here, let me give you one to try. So I'm just going to do a higher one to make a point. So how about 2 divided by the 4th root of 3? So rationalize the denominator. Give that a try. What you should do is multiply this by something. Same thing on the top and the bottom. But it's a 4th root. So you need the 4th root of 3 times the 4th root of 3 times the 4th root of 3. So I'm adding in 1, 2, 3 more, having a total of 4 because it's a 4th root. So I could write the 4th root of 3 times 4th root of 3 times the 4th root of 3 as the 4th root of 3 cubed. So hopefully you can see here that I have 1 3 here under a 4th root. And what I'm giving it is 3 more 3's under a 4th root. So that when I multiply these together, I'll have 3 to the 4th power under a 4th root. So cancel, cancel. Since I've done that there, I need to do that here as well. And now you just run some simplifying work. Right? 2 times the 4th root of 3 cubed is 2. 4th root of 3 cubed is 27. So I'll just write that as 27. 4th root of 3 times 4th root of 3 cubed is 4th root of 3 to the 4th, which means that the 4th root and the 4th go away, leaving me with just 3. And that's exactly why I did that, because now I have a rationalized denominator. Boom. If this had produced something that was simplifiable, you should do that. Okay, that's how you rationalize the denominator. So that's division. All right. Well, I'm going to call it there. We'll talk about addition and subtraction next time, and I'll tell you at that point how to solve radical equations, and then we'll just talk about some last-minute kind of things you can do with roots, like the Pythagorean theorem, and then we'll call it good on chapter 6. So, talk to you guys next time.